All right, we're going to finish up chapter 2 today. This is section 6, limits involving infinity and asymptotes. And they go together because once we start talking about what that means at limits going to infinity, then we'll see how they define asymptotes. The definition, let's look at the definitions first. All right, we say that f of x has the limit, this is on your sheet, you have to worry about it. Limit L as x approaches infinity, and we'll write it this way. The limit as x approaches infinity of our function equals L. If for every epsilon greater than 0, there exists an M such that for all x's in the domain, we know that f of x, absolute value of f(x) minus the limit, is less than epsilon whenever x is greater than some value m. That's for x going to positive infinity. Now we're going as x goes to negative infinity. We can write x goes to negative infinity of some function equals L. If for every epsilon greater than 0, we're going to use that symbol for there exists. And from now on, whenever we use for instead of for every, we'll use that. If for every epsilon greater than 0, there exists an n.
So that equals, that's going to be
That's for every, and this is there exists. Such that the absolute value of f of x minus L is less than epsilon when x is greater than n. I'm not greater than, that's an n, because we're going to the negative.
for spotting never.
Well, it would also, well, for any epsilon, there's some value m and n where this exists. As our function, x goes to positive and negative infinity. So first off, before we get an example, what does it mean as x goes to infinity? What does that mean? Yeah, it goes infinitely to the right. Whatever happens to the function, it happens further out. Because closer to 0, we see slower movement. We're interested in what happens to the function further on out, in positive and negative. Because a few things can happen. And we'll look at some of those examples in the very near sections. Example 1. Show that the limit as x approaches infinity of 1 over x is 0, and also show that the limit as x approaches negative infinity of 1/x also equals 0. So yeah, so you're right. We have to find an m and n values, but we also have to, if we know the value of epsilon, we also find it that way too. So to begin with, algebraically, as x goes to infinity, is this a true statement? What's the graph of our function? What's the graph of 1/x? Right. The closer it gets to 0, the bigger it gets, and the closer it gets to infinity, the lower it gets. And same thing with the negatives. So as x goes to infinity, what happens to the function? It gets closer, 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 closer to 0. It's approaching 0. So that's what that says. As x goes to negative infinity, the function gets lower or higher, higher, higher. It gets closer to 0. But that's not what the question is asking us to do. It says we have to show this using our definition. Graphically, we can see it. So A. So remember our definitions, we had the m and n. We had to find the m for the x goes to positive infinity and n when x goes to negative infinity. So we're saying that epsilon is greater than 0. That has to be true because it's a distance that we're getting closer to our limit value. We need to find an m where our function minus L is less than epsilon when x is greater than some value m. All right, so what's our function? 1/x. What's our limit? 0. That's our limit. So that equals absolute value of 1/x. And because of this, we know it's less than epsilon. So remember, in order to do this, we have to find this in terms of x so we can compare them. So this is 1/x. If we flip them, it'll be larger than. Because we have to compare the x's. If that's true, then m is equal to 1/epsilon. That's what I said earlier. If we knew what epsilon was, we could find the value of m.
Will it give us epsilon in some cases or?
Sometimes, yeah, remember earlier in this chapter, they gave us epsilon equal to this, find delta. So this was exactly the same reasoning.
No,
Is this delta? Is the M delta?
It's like it's serving as delta, yeah. And
that's
it
what M is serving as, or?
was, remember earlier it was x minus c is less than delta. But we can't use that because what is our c? We're going to infinity. So that's why we can't use the delta. But it's serving the same form as that. Yes. So that's for the M part. That's for X goes to infinity. Now we gotta look at for X. Now we gotta prove this. Same reasoning. So we have f of x minus L is less than epsilon when x is less than n. 1 over x is less than epsilon. Okay, now it's different. The setup has been the same. But for here, our x's are negative.
Is it 1 over negative x or is it negative 1?
It's the same thing. But yeah, so because we're going to negative infinity, we're using negative x's. So basically what we're saying now is 1 over x is greater than negative infinity. Or negative epsilon. And if we flip those, we get x is less than negative 1 over epsilon. Now we have our connection. So n is equal to negative 1 over epsilon. So that's how we found the m and n. Theorem 12. All the limit laws from theorem 1 are true. When C is replaced with infinity. So the limit as x approaches C of f of x equals L. The same rules hold as x approaches infinity. And we say plus or minus here. It doesn't matter. The same rules hold. So we're going to follow the same. We don't have to learn any more laws for those. I don't see why they made it a theorem. They should have said, here's a note. The same rules exist. Example 2. The properties in theorem 12 are used to calculate the limits in the same way as x approaches C. Okay. A, the limit as x approaches infinity of 5 plus 1 over x. So what property are we going to use here?
Like, or is this just?
Well, we use,
No, I was just looking at how close they were. And the others.
oh, no, yeah, it's supposed to be spaced. I forgot to tab it. So because of the 5 plus 1 over x, we use a sum rule. So the limit of a constant is that constant. The limit as x approaches infinity of 1 over x, we just saw that equals 0. So the answer is 5. The reason
Equals 5, or is it just the whole thing?
this whole limit equals 5. Because the basic theorem is this: the larger the denominator, the smaller the answer. In other words, 1 over 1 is bigger than 1 over 10, is bigger than 1 over 100, 1 over 1,000. So the bigger the bottom number is, the smaller the number becomes. So as it goes to infinity, it becomes so small, it disappears. So it goes to 0. B, the limit as x approaches negative infinity of pi radical 3 over x squared. Think of our properties here. Oh, no, here, no, because this is a constant. There's no x up there. So it can go out in front. Now this one, in order to be able to use a property, we can rewrite this as 1 over x times 1 over x. The limit as x goes to negative infinity of 1 over x times the limit as x goes to negative infinity of 1 over x becomes pi radical 3 times 0, which is 0. Did you have to go to these? No. We could have seen this one here also for the same concept. If 1 over x goes to 0, then 1 over x squared has to go 0 faster. Because whatever my denominator is, I square it. For these? But, well, if we look at the graph, as x goes to negative infinity, what y value are we getting close to? 0. So that's why it's 0. And just for that, as x, the bigger the bottom number gets, the smaller 1 over that number becomes. So that's why this becomes 0, that becomes 0.
Can it give us a different point as, I mean, I know we know that x versus infinity would say it was 1 instead of 0. Will it give us parameters like that, or?
Well, they did in the earlier sections. Because up until now, we've always had x goes to c or negative c. Now
I mean, now that we throw infinity into it, is it still possible to do that, or?
yeah, because up until now, we've done there are 3 possibilities. You can go to some value c, which is inside the domain. You can go to 0, or you can go to infinity. So
it's gonna be.
well, it has to be one of those 3, because when you get closer to 0, or in the c value you pick are where the asymptotes are. Where is the function undefined? What's happening at that point? That's what the c value is. It could be anywhere. In other words, if I had an equation 1 over x plus 2,
It'd be 0 plus 2, so
Yeah, well, the difference between, this is one over X. It's like this, one over X plus two has been shifted to the left two spaces. The same graph, it's just shifted to the left. But as we go to infinities, it's still gonna be zero. So that's the first part. Now we go to limits at infinity of rational functions. All right. I don't know what all you remember from algebra when you talked about asymptotes. Because that's exactly when you go to infinity or you look at functions like this, we're looking at asymptotes. Typically, whenever you have rational functions going to infinity, divide the functions. So do the division and see what happens. Let's look at example 3. The limit as x approaches infinity of 5x squared plus 8x minus 3, 3x squared plus 2. Okay, this is divide the functions by the largest x in the denominator. Divide. In other words, here we have, with the largest x on the denominator is x squared. So what this is telling us to do is divide each of these terms by x squared.
We don't use, we don't do the coefficient, we're just doing the X.
Deduct the x's because it's the x's that go to infinity. The coefficients really serve very little to us. Now simplify. So in the first one, the x squares cancel, so we just have 5. We have 8 over x minus 3 over x squared. 3, 2 over x squared. Now, as x goes to infinity, what happens to 8 over x? Where does that go? Yep. 3 over x squared. 2 over. So what we're left with is 5 over 3.
Um,
And well, I'll relate this back to algebra after you do this next one. Next, B is x goes to negative infinity. 11x plus 2. 2x cubed minus 1. What do we divide by? X cubed. So the first one is 11 over x squared. 2 over x cubed. 2, 1 over x cubed. As x goes to negative infinity, this one goes to 0. That one goes to 0. That one goes to 0. So we have 0 over 2, which is 0. Okay, let's go back to algebra. You're going to hate me because we didn't have to do all that proving stuff. What we've just labored to define as x goes to infinity, a negative infinity, are what we call horizontal asymptotes. Let's think about it. As x goes to infinity or x goes to negative infinity, it goes to 0, which is, in this case, that horizontal asymptote. It never crosses that line. So from algebra, I call it HA, horizontal asymptote. Remember, they're always dependent on the functions themselves. They could be any size polynomial. And on the bottom, I have BM. What matters whenever you deal with polynomials, the leading term is what dictates the shape of that curve. So the only part of this function, this polynomial, rational polynomial, that we're dealing with is the leading term. Three things can occur. If n is bigger than m, in other words, the exponent of the numerator is bigger than the exponent of the denominator. If that's the case, what happens? If there's more x's on top than the bottom, then the horizontal asymptote does not exist because it goes to infinity. Here's an example. X cubed over x squared. If I simplify this, I just have x. Remember, we're looking as x goes to infinity or negative infinity. Where does that one go as x goes to infinity? And infinity is not a number, so it doesn't exist. So if the top exponent is bigger than the bottom, there's no horizontal asymptote. If the numerator and the degree of the numerator and the denominator are the same, then the horizontal asymptote is simply the leading coefficients. Here's an example. 2x to the fifth over 3x to the fifth. Remember, anything smaller than that's irrelevant. X to the fives cancel, we're left with 2 over 3. And then the last one, if the top exponent is smaller than the bottom exponent, then the horizontal asymptote is 0. If the bottom exponent is bigger than the top, because the 2 of them cancel, which leaves us 3. As x goes to infinity, this one goes to 0. So we didn't have to, for those examples we just did, we didn't have to do any work. In this first one, the degrees are the same, so the answer is going to be 5 over 3. The bottom is bigger than the top, so the answer is going to be 0. Algebra. Example 4. Find the horizontal asymptote of the graph. As x goes to positive and negative infinity. Because you have to try both ways. It's the same as finding continuity. You have to find as x approaches from both directions. If you're looking to find the horizontal asymptotes or vertical or asymptotes, then you have to look at both going both directions. So what can you tell me here? Okay, but this is an absolute value down here. When x goes to positive infinity, what do we get? In other words, here, what we're saying here is x is greater than or equal to 0. what happens to this equation? Because they're the same exponents and the same x's. It's the coefficients, a over b equals 1. Mathematically, what we're looking for here is this: as x goes to positive infinity of this function, it goes to positive 1. Because they're the same size, so it's going to be the coefficients.
So the absolute value.
Not for that one. But now when x goes to negative infinity, now x is going to be less than 0. So we're going to negative infinity. Where's that one going to go? -1. Very good.
Does it matter?
Well, because if the absolute value wasn't there, then the negatives would cancel out. So since we're using only negative numbers and it's a cube, it's an odd exponent. So the top's going to be negative, the bottom's going to be positive, so the answer should be negative. So it's going to -1. Very good. Next example. Very good. Example 5. The x-axis is the horizontal slope of the graph given y is equal to ex. So the limit as x approaches negative infinity of e to the x becomes 0. Why? Because going to the negative infinity. So we can't do it mathematically. So let's go back to the first definition. We had f of x minus L is less than epsilon whenever x is less than some value n. So we have e to the x minus our limit 0, which gives us e to the x is less than epsilon whenever x is less than n. So since the x, we have e to the power n is equal to epsilon. We could solve for x by taking the ln of both sides, but the ln, we could have ln e to the power x is less than the ln of epsilon. So x is less than the ln of epsilon. So we're saying that ln of epsilon is equal to n. Because once we solve for x, we can just compare them. So that's our comparison. Example 6. A, find this one, the limit as x approaches infinity of sine 1/x. And B, the limit as x approaches plus or minus infinity of x sine 1/x. So for A, let's look at inside here. As x goes to infinity, what happens inside there? Right, so that becomes sine of 0, which is remember the unit circle? Sine deals with the y-axis. So at 0 degrees, this is 1 comma 0. Sine is 0. Cosine's 1. Okay, now this one. So we have to do two of them. We have to take the limit as x approaches positive infinity of x sine 1/x, and the limit as x approaches negative infinity of x sine 1/x. Don't think this one's as easy as it looks. Because let's look at this. Let's say that t is equal to 1/x, or any variable. Let's do substitution. So x sine 1/x would be sine t over t. Because it would be sine 1/x over 1/x, which is that. What is sine t over t? In section 1, the squeeze theorem. 1. So when it goes to positive infinity, it becomes positive 1. When it goes to negative infinity, because that's going to be negative also. Because it's going to that side, the sign values will be also negative, and the x value. Remember, if we're using x being negative, that, yeah.
Right, and all that X is equal to
Yes. Yes. Because that's what we did the squeeze theorem in section 1 or section 2. Now, what these find for us, remember, what we're looking for here as we're going to infinity, we're looking for horizontal asymptotes. So this graph at one will have a horizontal asymptote. So the graph of the second one will always be below there because we know what happens here. And then eventually it'll dampen off that way. So whenever we take the limit as x goes to infinity, we're looking for a horizontal asymptote. Example 7. Find the limit as x approaches 0 from the left. What'd you get? To begin with, what does the graph look like of e to the power 1 over x? Exponential function looks like that. If it's a fraction, then it looks like this. It's what? 0. By substitution, we could have said t is equal to 1 over x. So now we're looking at limit as t goes to infinity of the e to the t. So as it goes to infinity, because this is a rational, so as it keeps on going, it goes to 0. Ooh. So whenever you have 1 over x, it's try it with, and this is going to 0. Now this one will go to infinity. Example 8. Y equals 2 plus sine x over x, going from where to where. No, this is saying, using the sandwich theorem, find the horizontal asymptotes of the curve. Since it's looking for horizontal asymptotes, where am I taking my limits to? Positive, negative, infinity. So what we have to look at here is the limit as x approaches positive and negative infinity of 2 plus sine x over x. Now we're going to infinity, no longer one. So using the sandwich theorem, I say, yeah, sandwich theorem. So for sine x over x, gotta be positive because that's negative, negative. Because that's the maximum, could be one. So using the sandwich theorem as x goes to infinity, where does one over x go to? So as x goes to infinity, sine x over x goes to 0. So this example plus or minus infinity of 2 plus the limit as x approaches plus or minus infinity of sine x over x. That's 2. That's 0. Answer is 2. Can the function ever cross a horizontal asymptote? The answer is you'd think so, because asymptotes by definition means you can't cross, but no, horizontal asymptotes it can cross 1, 2, or 3 times. In other words, for example, this function. Actually, let's graph this one out. There's the graph. Remember, our answer was 2, so that's the 2 is the horizontal asymptote. Whenever a graph crosses the horizontal asymptote, it has to start approaching that. If it crosses once, it has to approach that horizontal asymptote. If it oscillates, it always has to get closer and closer and closer to that horizontal asymptote. So you see that eventually the graph becomes flat and becomes 2. So you see those values keep on oscillating and get small and closer and closer and closer to 2. Glad we did that. Okay, what was that? Let's look at example 9. This section is just trying to kill us with too many examples. Example 9. Find the limit as x approaches infinity of x minus the square root of x squared plus 16. What do you think happens to that function? It goes to infinity. Because as x goes to infinity, that goes to infinity. minus, this is gonna be smaller than this one. There's a square root minus, or 6 plus 16, and I square root it, so it's gonna be smaller. But can we do anything with it? What if we multiply by the conjugate? What is the conjugate in this case? X plus x squared plus 16 divided by x plus x squared plus 16. So that becomes a limit as x approaches infinity. On the bottom is just going to be that. On the top, we have x times x is x squared. These cancel. We have positive x radical x squared plus 16 minus x radical x squared plus 16 minus radical makes it x squared plus 16. These cancel. It's the difference of two squares. We have x squared. This negative makes it negative x squared minus 16. X squares cancel. Negative 16x plus radical x squared plus 16. So where is this one approaching? X is approaching infinity. If x is approaching infinity, how about this one, the function? Remember the three conditions. Look at the exponents of the x variable. This exponent is what? 0. This one is 1. So there's more on the bottom, isn't it? Since that's true, then it goes to 0. So the horizontal asymptote is the x-axis. So the conditions for horizontal asymptote, again, if n was bigger than m, if n is equal to m, and if n is less than m. So if the numerator is bigger than the bottom, does not exist. It keeps on going to infinity. If they're equal, then it's just the coefficients. And if the bottom has more, then it's 0. There's a twist to this. There's always the exception to the rule. F of x is equal to x squared minus 3, 2x minus 4. Graph that function. Do we have a horizontal asymptote? No, we don't. But we do have an oblique asymptote. We have what is called an oblique or slant asymptote. Oblique asymptotes occur when n is bigger than m by 1. In other words, if the exponent on top is bigger than the exponent on the bottom by 1, then we have what's called an oblique asymptote. How do we find the oblique asymptote? Because you can either have a horizontal or an oblique asymptote. You cannot have them both. To find the oblique asymptote, do long division. Only keep, no, actually, omit the remainder. Omit the remainder. So let's look what this means. Long division. Again, back to your algebra days. So we have 2x minus 4 goes into x squared minus, well, x squared 0x minus 3. You have to make sure all of the columns are allocated. What times 2x gives us x squared? One half x. Because 1/2 times 2 is 1, x times x is x squared. So 1/2, now we multiply 1/2 times that, so it's x squared. There is no x's. 1/2 times 4 is 2. So it's 2x. One half times 4 is 2x. It's a minus sign. Change the signs, add the numbers. What times 2x gives me 2x? A positive 1. So we have 2x minus 4. Change the signs. There's your remainder. We only want this part. That's your oblique asymptote. So what we would do there is we would graph this one. How would we graph that? Oblique asymptotes are always linear equations. Why? Why are oblique asymptotes always linear equations? Because that's the difference between the top and bottom. It's only bigger by 1. X to the 5th divided by x to the 4th is always going to be a single variable. So to graph this one, plot the y-intercept and follow the slope, up 1 over 2. So we know we have that asymptote. In order to graph this, we also have to look for what's called a vertical asymptote, which we'll get to also very soon. How do we find the vertical asymptote? Vertical asymptote is where the denominator equals 0. So we have 2x minus 4 so at 2, we have another asymptote, a vertical asymptote. Take the denominator, set it equal to 0, and solve for x. Again, you learned this in algebra. Now, there are only 2 possibilities this graph can go. It can either be in these corners or in these corners. How do we figure out which one it's going to be in? The best way? The only way, look for the x-intercepts. How can you find the x-intercepts of a function? Of a rational function? To find the x-intercepts of a rational function, set the numerator equal to 0 and solve. So our numerator is x squared minus 3, set it equal to 0. Square root, so we have x equals plus or minus the square root of 3. So it crosses the x-axis at positive radical 3. Well, we know positive radical 3 is less than radical 4, which is 2. So it's over here. There's 2. So it crosses right there somewhere. And at negative radical 3. So the graph will look something like this. Of course, you plot some points and you'll get a better picture of it. So far, so good? Again, that's everything we've done so far is from algebra, except the limit parts. Next topic. infinite limits. For example, our function that we've been talking about, 1 over x, the limit of our function as x goes to infinity, positive and negative, was what? What is this? 0. Because we're going that way. Well, what if we're going to 0 for this function? We have to look at it from 0 from the left, and we have to look at it from 0 from the right. Where is the function going as we approach 0 from the left?
Close to zero.
Negative infinity. It's going down. Right. As we get closer to 0, the graph is going further and further away. So it's going to negative infinity. As we approach it from the right, it's going up. So it goes to positive infinity. Those are infinite limits, meaning that they don't exist. They don't, but they're the values. Because infinity is not a value. Example 11. A. Limit as x approaches 1 from the right of 1 over x minus 1, and the limit as x approaches 1 from the left So what's the first one going to be? As x approaches 1 from the right. Which one? Let's look at this. We just talked about a graph that looks like 1 over x, right? It looked like this. All this one does is shift it 1 to the right. That's just the horizontal shift 1 to the right. So it's going to be the same values as this one. This side goes to positive, this side goes to negative infinity. Remind me also tomorrow to give you all the library of functions sheet, so we can always have that as a quick reference. Discuss the behavior of this function as x approaches 0. What does this graph look like? Nope.
Probably one where it's like something this and that. To, like, I mean, like this is curve like that.
You almost had it. Nope. This is squared. What is the square going to do to the numbers? This, if it's squared, but it's a denominator. It's x on the bottom.
That's one over X. Yeah, yeah.
Well, 1 over x looks like this. Right? That's 1 over x.
Is it from Tatum times B?
Nope. So why does it look like this? Because what happens to x if it's positive? Answer's positive. If x is negative, the answer's negative. Can this one ever be negative? It's the Atari symbol. If you square a negative, x can be negative, but if you square it, it becomes positive. So the limit as x approaches positive and negative infinity, no, it's going to zero, I thought. Going to zero. Positive, negative, zero. They both approach the same value, which is infinity.
Why?
12. So as x approaches zero from both sides, they both go to infinity, positive infinity. Example 13. It's got 6 examples. So the limit as x approaches 2 of this one, x minus 2 squared, x squared minus 4. Anybody just plug in the number? If you plug in 2, what happens? Just 0? What happens on top? What's happening on the bottom? 0 over 0. It's more, you can't just say happy it gets 0.
Sorry,
It's 0 over 0.
sorry.
If it's 0 over 0, what does that tell us we can do? Then something can factor out. So the top is x minus 2 times x minus 2. The bottom is a difference of 2 squares, x minus 2, x plus 2. Those cancel. Then the limit as x approaches 2 of x minus 2, x plus 2 becomes 0 over 4, which is 0. Then the next one is similar to that one, except the top is not squared. Because we get 0/0, we can factor more stuff out. The top is as far as it can go. The bottom is x plus 2, x minus 2. It's a difference of 2 squares. So we get the limit as x approaches 2 of 1 over x plus 2. Plug in 2, we get 1/4. The limit as x approaches 2 from the right, x minus 3, x squared minus 4. But what happens here? Look at the exponents. Nothing cancels. So if it's -1/0, it goes to where? 1 divided by 0. No. 0/1 is 0. So this one is undefined. Why is it undefined? Because how many times can 0 go to a 1? An infinite number of times. I can give you nothing infinitely, forever. I promise to do that. Right, and 1 does not fit the 0, so it goes into 0 times. So what happens here is, since there's more x's on the bottom, as x approaches 2, that means we have an asymptote, but which direction is it going? Anybody guess? Is it going? It's going to go to infinity. We know that because it's an asymptote. Is it going to positive or negative infinity? Because 2 is an asymptote, we know it's going to go to infinity. What happens to the top? If we plug in 2 in here, what's going to happen? It's a negative, because the bottom can never be negative. So that means we're going to negative infinity. D, limit as x approaches 2 from the left of the same equation. So what's this one going to happen? We're approaching 2 from the left. Because we're approaching it from 2 different directions, and it has 2 different directions. E. Oh, then this one's pretty straightforward. How about x going to 2?
It doesn't seem, no.
Mm-mm. This one should be pretty straightforward after what we've just done. What'd you get for E? As X approaches 2. Does not exist. For 2 reasons. For 3 reasons. If you plug in 2, what do you get? You get -1 over 0. How many times can 0 go into -1? Infinite, which is undefined, does not exist. That's the first one. Or remember, by definition, for this to exist, as X approaches 2 to be true, what has to be true? If this one exists, then it has to approach it from both directions. And they have to be the same value. Are they the same value? No. One's negative infinity and one's positive infinity to that same equation. Look at C and D. C goes to negative infinity and D goes to positive infinity. Since they're not the same thing, that limit doesn't exist. How about this one? How can we make them look the same? How can we make the 2 minus X, X minus 2 the same? If we factor out a negative here, then it's going to be X minus 2. Because X now becomes positive, 2 becomes negative.
Factor out one, see that they one over X squared.
Was it now we can cancel one of these out? Yeah. So we have the limit as X approaches 2 of -1 over X minus 2 squared. So it's going to be negative. And so where does this approach? Nope. Since 2 minus 2 is 0. 0 goes into 1 how many times? Infinite times. One more, and then we'll call it a day because we still have like 6 more examples. Find this limit as X approaches negative infinity of 2X to the 5th minus 6X to the 4th plus 1, 3X squared plus X minus 7. We have a total of 20. with what we've talked about so far, you should be able to just look at it and tell me. Look at the leading terms. What about the degrees of the polynomials? Look at the leading terms. That's 5, that's 2. If there's more on top, no. Goes to infinity. But since we're going to the negative side, it's negative infinity. 0 work. Okie doke, we'll stop there. We still have like 6 more examples to go, topics to discuss. We haven't discussed vertical asymptotes, so that's coming up, and precise definition.